everybody. Let's pray. In Jesus' name, thank you for the opportunity given to us. To say you give us knowledge and wisdom to our life, to be able to understand this course. In Jesus' name, I pray. Amen. Okay, so now I'm going to be taking electrical machines. We'll quickly run through the course. So now we are dealing with AC machines. For electrical students, we already done with these machines. You know the difference between AC and AC. Just AC is alternating from between positive and negative, while DC is just positive all through, that is a straight line. So now AC machines can be classified mainly into two categories: synchronous and asynchronous. So now a synchronous machine is an AC machine whose speed under steady state condition is proportional to the frequency of the current in its armature. So now what this is saying is that you know a, a machine now can be divided into two parts: the stator, right, and the rotor. The rotor is the rotating part, while the stator is the stationary part. So now the rotation takes place in the rotor. So now if the speed of the rotor is proportional, that is, it is equal to the speed of the magnetic field in the stator. That is, the speed of the rotor is proportional or is equal to the effect that it is given to the stator, then it is a synchronous machine. But in the case of asynchronous machine, now a perfect example of an asynchronous machine is an inductive any machine that has an inductor on it. So now it means for an asynchronous machine, the speed of the rotor will be less than the speed of the magnetic field in the stator. So now synchronous machine can be divided into synchronous generators and synchronous motors. So now the difference between generator and the motor, we all know that the generator converts mechanical to electrical and the motor converts electrical to mechanical. So now we are considering a generator here. So now they convert uh, mechanical power to electrical power. So now the construction now, in a synchronous generator, a DC current is applied to the rotor winding, which produces a rotating magnetic field. The rotor of the generator is then turned by a prime mover. This is, like I said the other time, a rotor is the rotating part of the generator. So now, let me point to a statement here. States that okay, the rotor of a synchronous generator is essentially a large electromagnet. So what is an electromagnet? An electromagnet is a material that becomes magnetic when electric current is passed through it. You get? So now, in this case, a DC current must be passed through the rotor for it to produce a magnetic field, which is an effect of the rotation. You get? So now, when a current is passed through the rotor, it rotates and produces a magnetic field. Now, the stator, which is enclosing the rotor, now we know what we call induction, right? So now, due to the magnetic field produced by the rotor, the windings on the stator will be induced. You get? and this induction will lead to um, the windings giving us voltage. You get? And in this case, due to the arrangement of the stator, we are going to have three phase set of voltages within the stator winding. Okay. Then now, two terms commonly used to separate the windings to describe the windings of a machine are field windings and armature windings. You already know that. Our field winding is the winding of the rotor, while our armature winding is the winding on the stator. So now it means the field winding is the winding to which the DC current is connected to for the rotor to be able to rotate. Then the armature winding is the winding that that's that is close to the rotor so that induction can take place for there to be voltage drops across the armature winding. The reason why I said voltage drops plural is because you're having three set of voltages because the stator is giving out um, three phase. You get? So now, okay, in general, the term field winding applies to the winding that produces the main. I've already explained that. So now for synchronous machines, the field windings are on the rotor. The terms rotor winding and field winding are used interchangeably. Yes, I already seen that. And similarly, the term armature winding and stator winding are used interchangeably. In the rotor of a synchronous generator usually utilizes electromagnet. Yes, I already said something on that. Then the magnetic poles on the rotor can either be salient or non-salient constructed. Now, what we mean by salient constructed and non-salient constructed is that in the construction of a rotor, now it is stated that a rotor is a large electromagnet. Yes. So now, normally a magnet has only two poles. That's theoretically, it has only two poles. But if you continue to break a magnet, to continue to produce multiple poles, just still revolving around the two poles. So now, what we mean by salient and non-salient um, pole arrangement is that now in some rotors, you can have your north and pole, your north and south revolving in alternating directions. Like your rotor is rotating, is the rotating part. So now the north pole can be alternating. The north and south pole can be alternating rather. North and south pole. So they can be alternating. Okay, when it is rotating, north will be here, south will be there. Then it gets to another point, north will be here, south will be there. When it gets to another point, south here, north here, you get. And in some cases, the north and south will be constant during rotation. So it will be constant during rotation. So now for salient, it will have different points where it can change. Different points where it can change. But for non-salient, it only has two alternating poles. That is north and south, and they remain constant. Just rotating in that manner. So now the DC current must be applied to the field current, like I said the other time, that it is an electromagnet. So for it to be magnetic, you have to apply the current through it. So now, okay, now if you are applying a current to the field winding, that is the winding on the rotor. If you are applying a current, if you are passing the current through it, now imagine you having an external DC source It is passing the current through the field winding. Now, and the rotor, remember the rotor is rotating. Hmm? So now, to avoid entanglement of the wire that passes the current through the from the DC source to the field winding now. So to avoid having any issue or entanglement of the wires, so now we must employ a special arrangement in order to avoid this problem. So now this can be done in two ways. One, supplying the DC power from an external DC source to the rotor by means of slip rings and brushes. So now we are going to explain that. Now slip rings are metal rings completely encircling the shaft of a machine but insulated from it. So now I'm going to show a picture to explain that. Okay. This one. Sorry. Okay, this is the picture. So now this is the picture. Okay. So now as you can see, this is the picture. Let me zoom it. Okay, this is the picture. So now as you can see, the slip rings, these are the slip rings. This is the shaft. The shaft is the part, just a rod. The shaft is just a rod connecting to the rotor. So as the rotor is rotating, the shaft is also rotating. So this is the shaft. You can see there the main shaft. So now the slip rings, as this explained here, that okay, that the slip rings completely encircling the shaft of the machine. You can see it here. These are the slip rings. Two slip rings, but they are insulated from the shaft because the slip ring, the slip rings, they are conductors, and the shaft is also a conductor. So to avoid losing power through the shaft, we insulate the slip rings from the shaft. Okay. So now, one end of the DC rotor winding is tied to each of the slip rings. Now, the slip rings, they are like conducting wires. You get conducting wires that transmits current now to the rotor. Now, from the explanation here, it says the DC rotor winding. So the DC rotor winding is tied to each of the slip rings. So now one slip ring is a connector, is like a wire to the rotor winding. And when I say rotor winding, I mean the field winding, right? That's the field winding. So now the second slip ring also is a connector to the other terminal of the rotor winding, that is the field winding, right? Okay, so now, and a stationary brush rides on each slip ring. Now the essence of the brush there is also for conduction. But now, if we are to attach the DC current, the external DC current now, the external DC source rather, the external DC source to the slip rings directly with the wires, when the shaft is rotating, there is 99% possibility that the wires will be entangled around the shaft. You get, so this will cause a problem, and eventually the wire will be stressed and it will cut. So now to avoid this, the brush now will just be slightly on the slip rings. So now the brush is made up of graphite, and we know that graphite is a conductor, right? And it's very soft. In order to avoid wearing of the slip rings, since the slip rings they are made of metals, right? So now the brush or the brushes now that will be on each slip ring as they seen in the picture. This is the first brush, this is the second brush now, right? So now these wires red and green, they are going to the external DC source. You get the external DC source. So now let me just explain this way. Okay,
Ma,
the external DC source. These are the wires, the green and red wires. So now the graphite is serving as a conductor through this metal, this slip ring, then to the field winding. The field winding is here. I guess the connection is done internally in this case. You get. So now, then this other wire through the graphite is going to the other slip ring, to the other terminal of the field winding. You can see it here, the field winding. You get. So now, since they are all conductors, so they are just like normal wires. But the reason why this arrangement is used is just to eliminate the problem I stated earlier. Okay, so now we are done with that. So I've already explained all this. Okay, so now the reason why this method is not used in some cases is that the amount of maintenance required on the machine, since the brushes must be checked very regularly. That is, the amount of the maintenance required on the machine is much, because your graphite is very very soft. Your graphite is one of the constituents of your pencil. So now imagine how soft the material in your pencil is. So that is how soft the graphite can be. So now imagine you rubbing it on a metallic surface. So now a lot of maintenance is required. So now number two, brush voltage drop can be the cause of significant power losses in machines with larger field current. So now imagine if the field current now, let me open that picture again. Oh, sorry. Sorry. Okay, sorry. I need this one. Okay. So now if the field current now, the current coming all the way from here is called the field current going into the field winding now. If the field current is much, and you know, regardless of the fact that graphite has a high conductivity, despite the fact that graphite is highly conductive, it still has little resistance. So now if a high field current is passed through it, now the voltage drop will be high, because regardless of the fact that your resistance is low, since your current is high and V is equal to IR, so now it's going to give us a high voltage drop, and this can if there's a voltage drop here now, it's going to be deducted or subtracted from the voltage that you'll be expecting at the field winding. So it will lead to loss. Okay, now despite these challenges, slip rings and brushes are used on all smaller synchronous machines because no other method of supplying DC is cost effective. Okay, on larger generators and motors, brushless exciters are used to supply the DC field current to the machine. Now, what is a brushless exciter? So the brushless exciter is a small AC generator with its field current, its field circuit mounted on the stator, and its armature circuit mounted on the rotor shaft. The three-phase output of the exciter generator is rectified to direct current by a three-phase rectifier circuit also mounted on the shaft. Okay, so now you might be wondering, why is it that in our normal generator now, said the rotor, or where we have the field winding, is the rotating part, and the stator, or where we have the armature winding, is the stationary part. But in this case, it's the field circuit of this, which is meant to be rotating now, is and the armature winding now, which is meant to be stationary, is mounted on the rotor that is rotating, that is vice versa. So now, the reason is that the rectifying circuit stated here is in form of rotation. You get? So now the rotation is what will aid the three phase that we are going to get. You get? So now for it to be rotating, for rotation to take place, you don't have to find another means to make rotation take place, since the shaft of the main machine is rotating. You get? So now since the shaft of the main machine is rotating, you just use that to rotate the three-phase rectifier circuit. And the three-phase rectifier circuit is connected to the stator. Remember, the stator is the part where the output is gotten, right? So now your AC input is going in through the field current, and the field current is on the stator, right? It's on the stator. So now there is an induction on the armature circuit mounted on the rotor. This is where you get the output on the armature. You remember, on the armature, this is where you get the output, right? So now, for you to be able to rectify it, you need a rotating rectifier. So now you mount where the output is coming out from, that is the armature circuit, on the shaft, so that when the shaft is rotating, the armature circuit is also rotating, and there is a contact between the output of the armature circuit, which is AC, and the rectifier, which is also rotating, in order to bring out a DC output. So now we are done with that. So now rectifying circuit also mounted on the shaft of the generator is then fed to, okay, by controlling the small DC current of the exciting. That's a normal thing. When you control the input current, you can also control, then you are controlling the output current. Okay, since there is no mechanical contact in the brushless machine, you can see it's brushless. So there's no brush that will be sliding across the slip rings. So there's no contact. So you have less concern on maintenance of this type of arrangement. So now there's another way to make the excitation of the generator completely independent of an external power source. Okay, a small pilot exciter is often included. Okay, so now according to what I read, we have a main exciter and a pilot exciter. Let me use this block diagram now to explain. Now, a pilot exciter is the one that receives the AC now. So now it transmits it to the main exciter. Then the main exciter is just like a rectifier that supplies the rotor now. Since the rotor needs DC, not AC, so a rectifier converts AC to DC. So now the main exciter converts it to DC, then it supply it to the rotor, and then the generator is working now. You can see generator, synchronous generator. So now the prime mover is the rotating part. You can see mover there. So now when the AC voltage is now produced, since we are dealing with a generator, it must definitely give us an output voltage, which is AC. So now when it is produced, it is a continuous process. So the AC will be supplied to the pilot exciter back, so that it can do the same thing and give the AC to the main exciter. Then the main exciter rectifies it to DC, then gives it to the generator. So now, okay, let me quickly run through. A synchronous generator's rotor consists of an electromagnet to which DC is supplied. The rotor's magnetic field points in, okay, what we have been explaining since is the same thing, points in the same direction. Same direction. Okay, a synchronous generator rotor consists of an electromagnet to which DC is supplied. The rotor's magnetic field points in whatever direction the rotor is rotating. Yes, and the rotor is rotating. So if the rotor is rotating in clockwise direction, the magnetic field is also moving in the clockwise direction. So now the rate of rotation of magnetic field machine is related to the stator's electrical frequency. So now a rotation that is due to the DC current applied to the rotor. The rotation that is produced now leads to an induced magnetic field on the stator. So now the induced magnetic field on this stator produces a frequency. And now we know the definition of frequency. Frequency is the number of cycles per second, right? So now the derivation of this formula, I'm going to display it quickly. I'm going to display it for better understanding. Okay, now this is it. This is it. Okay, so now we know that the frequency, okay, this is it. The frequency of a rotating material, of a rotating object now, so a rotating object now is the number of cycles per second, right? But now we can use mathematics to manipulate this. So now we can see if we multiply the number of cycles per revolution by the number of revolutions per second. So now revolution, we cancel revolution, so we are left with number of cycles per second. You get? So now we can use this. So now the number of cycles per revolutions now is our P. But now our P is in relation to poles. You get the poles that we have depending on the arrangement, maybe salient or non-salient now. So now the pole, the relationship between the number of cycles per revolution and the pole is that you can only get the number of cycles per revolution based on the pole, the arrangement of the pole that you have, or the number of poles that you have. You get? So now if the rotor is covering maybe 10 cycles per revolution. So now it means if it's covering 10 cycles per revolution, it means the number of poles it will take to complete 10 cycles per revolution now will be will be will be more than if we are having 5 circles per revolution. You get? So if you're having 5 circles per revolution, to just quickly go around the poles. So it means we have lesser number of poles. Then if we have more circles per revolution, it means we have more number of poles. I think you understand that. So now that's the relationship between your poles and number of circles per revolution. So revolution per second. This should not be new to mechanical students. Revolution per second. So now, in most cases, we consider revolution per minute, right? Revolution per minute. So now this is why we have N divided by S. Now the standard measurement is in revolution per minute, that is RPM. So now to convert it to revolution per second, you divide it by 60, right? You divide it by 60. Okay, now for you to convert it, divide it by 60. Sorry, you divide it by 60. So now the difference between P and capital P is that poles are in pairs, right? Poles, they are in pairs. So now for us to get the accurate measurement, we have to consider just a pole. So now for us to consider just a pole, you have to divide the pairs of poles by 2 to get a single effect of each pole. So now if you multiply these two, we have Pn over 120, which is the same formula we have in the note, right? Okay, sorry. So now this is it. So now the explanation is here. It says field poles and speed out. Okay, you can see our N is speed. I'm sorry, I made a mistake the other time. Speed in rotation per second and revolution per second rather. You can see it. Revolution per second. So our N is revolution per second, sorry. So now for us to convert it to revolution per minute, you divide by 60. So this is it. Okay. So now let's just continue. Let us to go fast. So now we all know all around the world the constant frequency that we operate is between 50 and 60 hertz. So now that's it. Okay, so now let me stop here for this video. We'll continue next time. Thank you.